It's a quiet morning in Batam, Indonesia, as the city awakens to a new day. But above, at 7,000 feet, something catastrophic is unfolding. The world's largest passenger aircraft, Qantas Flight 32, carrying over 400 passengers, is facing a disaster that will push its crew to the brink. One of its engines has exploded, and the damage is crippling vital systems, leaving the remaining engines struggling to keep the plane in the sky. The pilots hear two loud bangs from the left side, and the cockpit erupts in a flurry of emergency warnings. Pan, Qantas 32. Engine failure number 2. Maintaining 7,400 feet. Maintaining current heading. Stand by for instructions. These words, repeated over the radio, signify the beginning of an incredibly intense sequence of events. The crew faces a critical decision. Do they return to Singapore immediately, risking complete loss of control before landing, or continue flying and test the aircraft's systems, risking running out of fuel before reaching safety? As warning messages flood in, signaling possible fuel leaks and failures in flight controls, the tension rises. The aircraft's systems are failing fast, and every decision matters. This is a life-or-death situation. A small defect in the engine has ignited a catastrophic chain reaction. And now, over 400 lives depend on the choices made in these next moments. The story of Qantas Flight 32 begins on the morning of November 4, 2010, when the Airbus A380 taxis for departure at Singapore's Changi International Airport. The flight, bound for Australia, is a routine stopover for Qantas on their flagship London to Sydney route. The aircraft is fully loaded with 440 passengers, 24 cabin crew members, and 5 pilots, led by Captain Richard Champion de Crespigny. With over 15,000 flight hours, Captain de Crespigny is a veteran with unparalleled experience. He is joined by First Officer Matt Hicks with 11,000 hours, and Second Officer Mark Johnson with 8,000 hours of flight time. The flight deck is further supervised by Captain Harry Webben, who brings 20,000 hours of experience, and check Captain David Evans, who has a solid 17,000 flight hours. At 9:56 a.m., Flight 32 takes off from Singapore, climbing steadily to cruise altitude. Everything seems routine, until 5 minutes into the flight, when the first signs of disaster strike. As the aircraft climbs through 7,000 feet, a terrifying noise fills the cockpit. 2 loud bangs come from the left side. The crew immediately checks their instruments. The left engine has exploded. Investigators later discover that a turbine disc failure caused the explosion, which set off a chain reaction, rupturing hydraulic systems and damaging critical components. This wasn't just an isolated engine failure. The explosion led to massive damage to the aircraft's systems, including a complete loss of control in flight systems and a major failure in the fuel lines. This incident was not the first of its kind. Similar engine failures had occurred on other Airbus A380s, but the level of damage on Flight 32 was far more severe. For instance, in 2008, an Airbus A380 had experienced an engine malfunction, but the redundancy systems in place had helped stabilize the aircraft. However, in this case, even the advanced redundancy systems failed to fully prevent the catastrophic damage. As the crew scrambles to control the aircraft, they face the impossible decision of whether to return to Singapore immediately or remain in the air to assess the systems further. The NTSB and ICAO stress the importance of redundant flight control systems, and while the A380's design was meant to handle such failures, this situation revealed the limits of even the most sophisticated technologies. The crew, composed of highly experienced pilots, faces these decisions with the weight of over 400 lives on their shoulders. The question is no longer just about flying the plane safely. It's about survival. Should they trust the aircraft's failing systems to get them back to safety, or should they turn around before it's too late? With each passing moment, their options are shrinking, and the clock is ticking down on their ability to make the right call. As the Airbus A380 banks to the left, signaling a potential engine failure, The first warning message arrives on the aircraft's electronic centralized aircraft monitoring (ECAM) system. It's clear now that something is wrong. The turbine inside engine number 2 has overheated, and the situation is deteriorating rapidly. Captain de Crespigny, maintaining his calm, decides to level off the aircraft at 7,400 feet and 250 knots. But even as he begins to regain some semblance of control, another problem surfaces. The auto-throttle system has stopped working. It's another hurdle to overcome, a sign of deeper troubles ahead. The captain programs the autopilot to maintain the altitude and speed while he begins to assess the situation further. Once satisfied that the aircraft is under control and stable, he directs First Officer Matt Hicks to start addressing the ECAM warnings. The crew is now fully engaged in handling the critical malfunction. Following the checklist for an overheating turbine, the crew moves the thrust lever for engine number 2 to idle and monitors the engine's response for 30 seconds. They are now in a race against time. As the seconds tick by, they decide to transmit a pan-pan message to air traffic control. This is not a mayday call, which signals an immediate emergency and the need for a rapid landing. Rather, a pan-pan message indicates that there is urgency and a potential need for assistance, but it doesn't require an immediate landing. Pan-pan, Qantas 32, engine failure number 2, maintaining 7,400 feet, maintaining current heading, stand by for instructions. Captain de Crespigny transmits, ending the call with a request to stand by. This gives the flight crew the space to deal with the aircraft without interruption, following the mantra that every pilot learns early in their training: aviate, navigate, communicate. But just moments later, the ECAM system flashes another alarm. There's a fire in engine number 2. The warning is brief, just 3 seconds, but that's enough to send a chill through the cockpit. The pilots, now fearing the worst, decide to shut down the engine and discharge the fire extinguisher bottles installed within. They discharge the first fire bottle twice, but there is no confirmation that it has been successful. A second fire extinguisher bottle is tried, but again, there's no sign that it has been deployed. Confused but determined, the crew presses on with the emergency procedure for an in-flight engine shutdown and begins transferring the fuel from engine number 2. They quickly review the engine indicators. Engine number 2 is confirmed as completely failed. Engines 1 and 4 are running in a degraded mode, and engine 3 is in an alternate mode. The degraded and alternate modes indicate that the onboard computers are no longer receiving critical engine parameters, and while the engines are still producing power, the pilots now have to manually control them, something that the aircraft's automated systems were designed to handle. Meanwhile, inside the cabin, the situation begins to unravel. Passengers seated on the left side of the aircraft can clearly see the wing has been damaged, and fuel is pouring out of the wing. One passenger even notices a small fire inside the wing. Anxiety quickly spreads throughout the cabin as the reality of the situation sets in. The flight attendants are visibly concerned. One of the cabin crew members rushes to the intercom, desperately trying to reach the flight deck. However, despite their repeated attempts, there's no response from the cockpit. The pilots are overwhelmed, consumed by the flood of ECAM alerts and warnings related to other critical systems. As the situation worsens, the cabin crew continues to try to communicate with the flight crew, but the pilots remain too engrossed in managing the aircraft's deteriorating systems to notice. Every few moments, a new ECAM alert pops up, showing failures in fuel, flight controls, electrical systems, braking, and hydraulics. The aircraft, once a symbol of engineering marvel, is now a collection of malfunctioning systems, and the pilots are forced to operate with manual control as the clock ticks down. Out of the 22 total systems on the aircraft, 21 are malfunctioning. For any pilot, this is the worst nightmare come true. It's becoming increasingly clear to Captain de Crespigny that the situation has escalated far beyond a simple engine failure, as would be covered in routine airline pilot training. This is no longer a manageable scenario. Something much more serious is unfolding. Yet, even as the gravity of the situation sinks in, the crew is still unsure of the exact cause. The clock is ticking, and the crew is facing their first of many difficult decisions. Should they attempt an immediate landing or address the numerous critical failures first? Attempting a landing with the aircraft in its compromised state could prove disastrous, especially with the flight controls possibly malfunctioning. However, staying in the air with an active fuel leak also comes with its own dangers, including the risk of engine failure or a catastrophic loss of fuel. It's a tough spot for Captain de Crespigny, who must weigh the risks carefully. After a brief discussion, the crew reaches a decision. They will stay airborne. They are confident that they have full control of the aircraft and enough fuel to remain aloft while they continue troubleshooting and addressing the many failures that have flooded the ECAM system. But time is of the essence. The captain decides to make a public announcement to inform the passengers of the situation and to maintain calm. This is your captain speaking. As you may be aware, we've experienced an issue with one of our engines shortly after departure. I want to assure you that the aircraft is stable, and we have full control. We're currently working through a number of checklists with our team, and we have sufficient fuel and systems to remain airborne while we assess everything thoroughly. At this stage, there is no immediate cause for concern, and we'll keep you updated as we go. We appreciate your patience and calm. Thank you. As the flight crew continues working, First Officer Matt Hicks contacts Air Traffic Control to update them on the situation. He requests directions for holding near the airport, and ATC instructs Flight 32 to fly a 20 nautical mile racetrack holding pattern just east of Changi Airport. Meanwhile, the crew is informed that aircraft parts have fallen to the ground, with fragments of the turbine disc landing in Batam, Indonesia, and hitting residential buildings and city streets. Miraculously, no one on the ground is injured. The news spreads rapidly, and rumors fly that a Qantas super jumbo jet has crashed over Indonesia. However, official confirmation is still lacking. Before diving into the crew's next steps and the outcome of the incident, it's crucial to understand the root cause of the engine failure. As the crew can only speculate at this point, it's important to look back at the engineering failure that triggered this catastrophic event. It all started with a misalignment in the manufacturing process of engine number 2. An oil feed stub pipe, designed to transfer oil within the engine, was drilled unevenly, making it thinner on one side. Over time, the thinner side of the pipe developed a fatigue crack, which eventually allowed a significant amount of oil to escape into the hot engine. The hot engine, operating at extremely high temperatures, ignited the oil, causing an internal explosion. The force of the explosion was enough to break apart one of the turbine discs, which was rotating at incredibly high speeds. The fragments of the turbine disc tore through the engine casing, puncturing the wing and fuel tank near engine number 2. The damage didn't stop there. Wires inside the wing were also severed, further complicating the situation. One of the hot turbine fragments broke through the wing's fuel tank, igniting fuel vapors inside the tank, resulting in a small fire. The damage didn't end with the fuel tank. The wiring severed in the wing caused a loss of monitoring capabilities for key systems, including fluid level, pressure, and reservoir air pressure for the green hydraulic system. This forced the crew to shut down that hydraulic system, according to the EAM checklist. As a result, many aircraft controls were no longer functional. These included the wing slats, outboard ailerons on both sides, some landing gear brakes, and about half of the wing spoilers. Although the aircraft flaps, elevators, and rudders remained operational, the situation was dire. Despite this, the second hydraulic system remained partially functional, with some pumps still operational. After entering the holding pattern east of Singapore, the flight crew begins the painstaking process of troubleshooting the aircraft's numerous failures. Over the next hour, they go through over 100 checklists queued in the ECAM system, addressing one fault after another. Meanwhile, the second officer leaves the flight deck to visually assess the damage to the wing. As he moves through the cabin, A fellow Qantas pilot, who is a passenger on the flight, shows him a live feed from the tail-mounted camera, available to all passengers via the in-flight entertainment system. The camera feed reveals a large streak of fuel pouring from the left wing, confirming the crew's suspicion of a fuel leak. The second officer then approaches the middle section of the cabin and notices several holes in the wing, further heightening the concern. As he returns to the flight deck, the second officer describes the extent of the damage to the rest of the flight crew. The situation is grim. The aircraft is in far from ideal condition, and the success of their recovery will depend on the crew's ability to cooperate and make the right decisions. It's a race against time, and every move they make will either bring them closer to safety or closer to disaster. In this critical moment, Captain de Crespigny understands the importance of ensuring that every member of his crew shares an accurate mental model, a clear and unified understanding of the situation. To accomplish the impossible, the crew must be aligned in their thinking. Drawing on his experience and lessons learned from NASA's Apollo 13 mission, Captain de Crespigny decides to invert the logic. Instead of focusing on what doesn't work, they will focus on identifying what still works. By narrowing their focus to the aircraft's functioning systems, they can make informed decisions and increase their chances of success. Through their review of the aircraft's system displays, the crew discovers a troubling reality. 8 out of the 11 fuel tanks are now unusable. Additionally, at least half of the fuel pumps have failed, including the fuel jettison pumps, which could have allowed the aircraft to release some fuel, reducing its total weight and bringing it below the maximum landing weight. Despite these failures, the crew determines they still have at least 2.5 hours of fuel left in the remaining usable tanks. With the fuel issue somewhat under control, the next task is to assess the controllability of the aircraft. While the crew is able to maintain level flight for now, the wing has been severely damaged, and the status of the control surfaces is in doubt. Due to the shutdown of the green hydraulic system, which powers many of the aircraft's control surfaces, the crew faces a 65% reduction in roll control. This means they have limited ability to bank the aircraft left or right. This kind of control malfunction is something that military pilots are specifically trained for, especially in cases where their aircraft may be hit by a missile or involved in a mid-air collision. Drawing from his extensive Air Force background, Captain de Crespigny decides to perform a control check of the aircraft before attempting the landing. It's crucial for him to understand how the plane will behave at lower speeds, especially with the landing gear and flaps extended. This is vital because any difficulties with the aircraft's handling are better addressed at a higher altitude, where there is room for recovery, rather than during the critical moments of final approach. Captain de Crespigny begins moving the side stick from side to side in various flap configurations. He carefully monitors the deflection of the control surfaces using the onboard monitors, checking for responsiveness. After a few tense moments, he is satisfied with the results. The aircraft seems manageable, and they can now begin preparing for an attempt to land the heavily damaged airliner. Next, the crew turns their attention to the critical task of calculating the approach speed and the minimum runway length required for landing. Using the onboard computer system, they work through the calculations. The senior check captain encounters some initial difficulties, but eventually completes the calculations. The results are sobering. In its current state, the aircraft will need nearly the entire 4,000-meter runway for landing, leaving just 130 meters, or about 400 feet, of runway to spare. This narrow margin means that the landing must be executed with precision. There is little room for error. Recognizing the gravity of the situation, the flight crew informs air traffic control that they are ready to land and request a long approach. ATC provides specific heading instructions, and the aircraft is vectored to fly further north before making a turn and beginning its 20-mile-long final approach to runway 20 center. While a typical final approach would begin around 10 miles from the runway, this extra 10 miles gives the crew additional time to prepare. The additional distance is crucial because the aircraft is in an abnormal landing configuration. The fuel imbalance, caused by the leak in the left wing, means the aircraft is heavier on one side. This adds complexity to the landing, as it affects the plane's balance and handling. The damage to the hydraulic system prevents the leading edge slats from extending, and the wing flaps can only be extended to position 3, far less than the usual full setting. As the aircraft turns onto the final approach course, the crew faces yet another challenge. The aircraft's landing gear needs to be extended. With no power from the hydraulic system, the crew uses the alternative method of gravity to release the landing gear from the up position. Now, with everything set up for the landing, the flight crew gives the cabin crew the command to prepare for arrival. With 3 engines still operational, the captain adjusts the thrust symmetrically on the outboard engines, numbers 1 and 4, while using engine number 3 to manage the aircraft's speed. Every move is critical, and the crew knows that the next moments will test everything they've trained for. Only the inboard engines on the Airbus A380 are equipped with thrust reversers, which means that engine number 3 is the only one on the aircraft that can provide reverse thrust to help slow the aircraft down after landing. As the aircraft descends toward the runway, Captain de Crespigny is faced with yet another tough decision. At 800 feet, the autopilot is disengaged, and the captain takes over, hand-flying the approach. The aircraft is descending at a rate of 1,400 feet per minute, close to double the maximum vertical speed for which the landing gear is certified to handle. The captain realizes that any misstep here could be disastrous. If he reduces the rate of descent too much before touching down, the aircraft could float above the runway for too long, reducing the amount of runway left for the rollout after landing. On the other hand, if he descends too quickly and lands too firmly, there is a significant risk of breaking the landing gear, puncturing the wings, and skidding down the runway, with sparks flying dangerously close to the leaking fuel. A catastrophic situation waiting to happen. Drawing from his wealth of experience, Captain de Crespigny makes a bold decision. Just before the wheels touch the runway, he pushes the control stick forward. Although this action may seem counterintuitive, especially during the flare, it rotates the aircraft around its center of gravity, lifts the main landing gear, and creates an additional cushion of air. This helps slow the descent rate, holding the aircraft in the air for an extra second and minimizing the impact on the landing gear. At 11:46, Flight 32 touches down on Singapore's runway 20 center, the very same runway from which it had taken off only 2 hours earlier. The aircraft deploys only half of the speed brakes, and with just one working thrust reverser, the captain applies maximum braking, hoping to slow the overweight aircraft before the runway runs out. Outside the airport, emergency services have blocked the perimeter road to minimize the risk of injury or death in case of a runway overrun. However, the biggest concern remains the 469 lives inside the A380 as it speeds down the runway, the end rapidly approaching. Despite the limited braking and the challenges of having only one functioning thrust reverser, the massive aircraft comes to a stop just 150 meters, roughly 500 feet, from the end of runway 20 center. It's a remarkable feat of precision and skill, demonstrating the captain's ability to handle the situation with calm and expertise. Once the aircraft comes to a complete stop, the cabin erupts in relief, with passengers breaking into applause. But the flight crew knows that the situation remains tense. The engines are shut down, but the onboard information display reveals that the temperature of the left landing gear brakes is over 900 degrees Celsius and rising. Fuel is still actively leaking from the left wing tank, and the risk of a fire or explosion is growing by the second. In a race against time, the flight crew contacts emergency services, who are already on standby, and requests firefighting foam to cover the fuel leak and the hot landing gear. The fire brigade responds promptly, but they request that the crew shut down engine number 1. The crew, still in disbelief, verifies that all engine switches have already been turned off. But as Captain de Crespigny glances out of the left window, He is shocked to see that engine number 1 is still running. Confused, but determined, the crew attempts several emergency shutdown procedures, but the engine continues to operate as if entirely disconnected from the rest of the aircraft. It appears that the engine and its wiring have been completely severed from the aircraft's systems. With the fire crew covering the fuel leak with foam and spraying water over the hot brakes to cool them down, Captain de Crespigny assesses that the risk of explosion has been reduced. At this point, there is no immediate need for an evacuation. As the situation stabilizes, the passengers begin to disembark using the air stairs provided by the airport. Meanwhile, the flight crew continues their efforts to shut down the last remaining engine, pulling circuit breakers to cut off electrical supply to various aircraft systems, and reconfiguring the fuel system in a desperate attempt to stop the flow of fuel to engine number 1. The situation is far from over, but the crew's swift, composed actions have ensured that the worst has passed. They continue working, but with each passing moment, it becomes clear that their handling of this crisis has saved not only their own lives, but also the lives of 469 people on board. Despite their best efforts, nothing seems to work in shutting down engine number 1. With no other options left, the flight crew makes the ultimate decision: to drown the engine in foam and water. For over 3 hours after landing, the fire crew continuously sprays foam and water into the engine. Finally, at 2:53 p.m., more than 3 hours after the harrowing landing, the last running engine on Flight 32 is shut down. The crisis is averted. Following the dramatic events of Flight 32, Qantas made the difficult decision to ground its entire A380 fleet for nearly 3 weeks, while the cause of the uncontained engine failure was thoroughly investigated. The airline, along with Rolls-Royce, the manufacturer of the engines, was concerned that other aircraft in the fleet might have been similarly affected. Rolls-Royce quickly instructed all operators to inspect engine turbines for signs of oil leaks before their next flights could take off. In response to the failure, Rolls-Royce also proposed a long-term solution, a software update that would include the addition of an intermediate pressure turbine overspeed protection system. This system would monitor the turbine disk's speed and automatically shut down the engine before the critical speed could be reached, preventing further catastrophic failures. The story of Qantas Flight 32 serves as a stark reminder of how even the smallest errors in design and manufacturing can snowball into a devastating crisis. Captain de Crespigny's quick decision-making, along with his extensive knowledge and calm under pressure, were absolutely vital in navigating the flight's many challenges. In one of the post-accident interviews, he rightly stated, "We must commit to a lifetime of learning." This valuable piece of advice holds true not just within aviation, but across all industries, emphasizing the importance of continuous improvement and learning from every experience. Thanks to Incog for sponsoring this video. Don't forget to click the link in the description to get an amazing discount.